Greetings of the day to all of you. Well, today I'm going to deliver a lecture on uh, controlled flywheeling or controlled freewheeling in a single phase full converter fed DC motor drive. Of course, separately excited DC motor drive. So, this is lecture number 13, and the lecture is about controlled flywheeling or controlled freewheeling in a full converter fed DC drive. As you already know, we have already discussed about a single phase full converter fed separately excited DC motor drive in early lectures. The power circuit diagram is like this. This is our single phase fully controlled converter or single phase full converter. These are the devices or thyristors T1, T2, T3 and T4. This is the AC source. Vs equal to Vm sin omega t is the supply voltage or source voltage, and Is is the source current. And this is the model of separately excited DC motor. This is armature circuit resistance Ra, armature circuit inductance La, and this is the back EMF of the motor Eb. So this is our DC motor model, which in this case is a separately excited DC motor. The motor armature voltage or the load voltage is Va, and load current or armature current is Ia. We have already studied in one of the early classes that when the converter is operating in rectification mode of operation, we get waveforms something like this at a particular delay angle. This is the nature of waveform that we get. This is for rectification mode of operation. And for inversion mode of operation, the waveforms are like this, something like this. Now, as you can see, whether we operate the machine or whether we operate the converter in rectification mode or in inversion mode, the load voltage waveform or armature voltage waveform has a positive segment as well as a negative segment in both the cases, whether the machine is operating in motoring mode or in regeneration mode, or whether the converter is operating in rectification mode for alpha less than or equal to 90 degrees, or it is operating in inversion mode for alpha greater than 90 degrees. Now let us consider rectification mode of operation. In the rectification mode of operation, you get the large positive segment of load voltage. You get the large positive segment of voltage across the load, say for positive half cycle of source voltage when T1 and T3 and this pair of devices is on. See, when this pair of devices is on, the load gets directly connected across the source via T1 and T3, and it receives the source voltage. So in the process, it receives a large segment of positive half cycle of source voltage and a small negative half segment of source voltage. And as far as current is concerned, current is constant. Current is unidirectional. That means this is the armature current Ia, this is the armature voltage Va, which means that although the load voltage or armature voltage reverses its polarity, the armature current or load current is unidirectional. It does not reverse its polarity, which means that from alpha to pi, armature voltage is positive, current is also positive, so power is positive. That means power is flowing from source to load via T1, T3 pair of devices, say in the positive half cycle of source voltage. And in the negative half cycle of source voltage, again same thing repeats. Power flows from source to load via the other pair of devices, that is T2, T4. Since we are considering the positive half cycle of source voltage, let us concentrate on T1 and T3 pair of devices. So load gets connected directly across the source. It receives large positive segment of voltage and small negative segment of voltage. From alpha to pi, since the voltage is positive, current is also positive, power is positive. That means there is the flow of power from source to load. And what happens to the power when it is received by the load? A small power is wasted as Ia square Ra loss in the armature resistance, and then some power gets stored in the inductance, armature circuit inductance, in the form of magnetic field, and rest of the power is converted into mechanical power which drives the load. This is what happens from alpha to pi. What happens from pi to pi plus alpha? From pi to pi plus alpha, the source voltage has already reversed its polarity. Since load voltage is same as source voltage, load voltage becomes negative. So from pi to pi plus alpha, a small negative segment of voltage is there. Since armature current is positive, but armature voltage becomes now negative, what is armature power? Power is voltage into current. Since voltage is negative, current is positive, so power is negative. What does negative power mean? Negative power means that this inductor, which had stored energy from alpha to pi, it is now releasing that energy. And where is that energy going? That energy is fed back to the source like this. Okay, it is fed back to the source via T3 and T1 like this. So therefore, from alpha to pi, power is delivered from source to load. A major portion of this power is converted into mechanical power which drives the load. Small power is wasted as I square R loss in the armature resistance, and some power gets stored in the inductance in the form of magnetic field. And from pi to pi plus alpha, power becomes negative. Negative power means that whatever power was stored in the armature circuit inductance, this inductance is releasing that power. And where does that power go? That is fed back to the source. So therefore, during these negative voltage segments, there is the power which is fed back to the source. And during the positive segments of the voltage, there is the flow of power. There is the flow of power from source to load. And during these small negative segments, there is the reverse flow of power from load to source. Actually, during this alpha to pi, a large amount of power flows from source to load, and a majority of that power, or maximum of that power, is converted into mechanical power, except for small I square R loss and small power which is stored in the inductance. And whatever power is stored in the inductance during the negative segment of the voltage, that inductive power is fed back to the source. So doesn't it mean that this is the flow of reactive power? During the from alpha to pi, inductor stores the energy, small energy, okay, and from pi to pi plus alpha, it releases that energy, supplies back to the source. I repeat, from alpha to pi, small energy flows from source to load, which is stored in the inductance. I'm talking of energy of the inductance only. I'm not talking of mechanical energy or I square R loss energy. A small energy flows from source to load from alpha to pi. I mean, a small amount of energy flows from source to inductance, and it is stored in the inductance. And during the negative segment of the load voltage, pi to pi plus alpha, this energy which was stored in the inductor, it is released and it is sent back to the source. So therefore, what is this energy which flows from source to load during positive segment of the voltage, and load back to source during negative segment of voltage? This is nothing but reactive power, because we know that reactive power just shuttles between source and load. It flows from source to load and then again flows back from load to source. Okay, so that means there is the flow of reactive power, and because of this flow of reactive power, if you find the input power factor, the power factor on the input side, AC side of the converter, it will affect the power factor will become poor. Okay, this happens during rectification mode of operation, and this also happens during inversion mode of operation. In the inversion mode of operation, the average load voltage is negative. Okay, so there are large negative segments of voltage and small positive segment of voltage. Now this small positive segment of voltage means that energy gets stored in the inductance from this point to this point, and during this period, whatever energy was stored in the inductance, that is supplied back to the source. That means in the inversion mode of operation also, there is the flow of reactive power. See, there is the flow of electrical useful power which is converted by machine into mechanical power. I'm not talking of that power. I'm talking of the power which is stored in the inductance in one half in one quarter cycle or in one period, one interval, and then in another interval that is supplied back to the source. So therefore, there is the flow of reactive power in the inversion mode of operation. Okay. The question is, can we stop the flow of reactive power between source and load? In other words, when there is the flow of power from source to load, a small power gets stored in the inductance. And then instead of that reactive power flowing back to the source, can we make that freewheel in the load circuit only, so that that is consumed by the motor and that power is also converted into mechanical power? Is it possible? If we can do that, then that means there will be no flow of reactive power between source and load. And then we can improve the supply side power factor also. Okay, can we do that? Answer is yes. How? If we just cancel, if you are able to cancel during the in the rectification mode of operation, if you are able to cancel this these negative voltage segments, and in the inversion mode of operation, if we are able to cancel these positive voltage segments, then we will be able to utilize this reactive power of the inductance and convert that into useful power, so that that power does not flow back to the source, thus deteriorating the source power factor. That power is also utilized by the motor and converted into mechanical energy. In other words, our load voltage waveform can become, it should become like this. So no negative segments will be there. Earlier there was negative segment. If we cancel that negative segment, what does this waveform tell us? It tells us that during the rectification mode of operation from alpha to pi, there is the flow of power from source to load L. Maximum of that electrical power is converted into mechanical power, which drives the load. A small power is wasted in the armature circuit resistance as Ia square R loss, copper loss, and some power is stored in the inductance, armature circuit inductance. And then from pi to pi plus alpha, our load voltage is not negative, it is zero. Okay, load voltage becomes zero. So this is the current, this is the armature current. Since load voltage becomes zero, okay, so that means, and it is not negative, that means whatever power was stored in the inductance, that is not supplied back to the source, because there is no negative segment of the voltage. Rather, we either this pair of devices or this pair of devices provides the freewheeling path for that energy. And when the inductor releases that energy, current flows either this through this pair of devices, through the load, or through this pair of devices. So this is called flywheeling or freewheeling. And then what will happen to that energy released by the inductance? Since we are not supplying that back to the source, we are freewheeling that in the load itself, either through this pair of devices or through this pair of devices. That energy will also be converted into useful mechanical energy by the motor. This we can do in rectification mode of operation, and this we can do in inversion mode of operation also. In the inversion mode of operation, the positive segments of voltages have to be cancelled. And in the rectification of mode of operation, the negative segments of voltages have to be cancelled. And what will happen during these periods? During the periods we cancel the negative segment or positive segment of voltage, freewheeling will take place. So let us discuss how we can achieve this and how we can improve the power factor of the drive. Okay, so let us first of all consider a normal waveform without freewheeling. This is our source voltage waveform. 0 crossing 0, pi, 2 pi, 3 pi, and so on. Let us assume we operate our drive in the rectification mode of operation, and let us assume continuous conduction mode of operation. We will take case A. Case A is rectification mode of operation. Rectification mode. And in this rectification mode also, the drive will either operate in continuous conduction mode or discontinuous conduction mode. Let us consider first CCM, that is continuous conduction mode of operation. In the continuous conduction mode of operation, if this is the back EMF of the motor, let us fire pair of devices somewhere here, and then another pair of device here, another pair of devices here, and current will be rising. When a pair of devices is fired, it will reach maximum value somewhere here, and then it will start falling. But before it becomes zero, another pair of device fired, and current again rises, then again falls, then again rises, then again falls. So that means current is continuous. This is the armature current IA, or load current, which is continuous. So this is continuous conduction mode of operation. And in the continuous conduction mode of operation, the firing pulses are, during the positive half cycle of source voltage, T1 and T3 have to be fired. And we fire T1 and T3 after a delay of alpha electrical degrees, say somewhere here. So firing pulses have to be issued to the gate terminals of thyristors T1 and T3 simultaneously. So this is the gating pulse after a delay of alpha electrical degrees to thyristors T1 and T3. So this gating current pulse is Ig1, Ig3. Ig1 means gate current pulse of thyristor T1, and Ig3 means thyristor T3. Since both have to be fired simultaneously, so a single pulse can be applied to both the devices. This is for positive half cycle of voltage. And for negative half cycle of source voltage, the other pair of devices has to be fired. The other pair of devices will be fired from pi plus alpha to 2 pi plus alpha. That means from this instant to this instant. From this is Ig2, Ig4. That means gating pulse of thyristors 2 and 4. Okay. Now, that means previously also, before T1 and T3 was fired, previously also T2 and T4 were fired. Okay. If we assume previous conduction also. Now let us see the waveforms. We have already analyzed this. We have also drawn these waveforms in one of the early lectures. I am just repeating. Now what happens at alpha? At alpha, T1 and T3 pair is fired during the positive half cycle of source voltage. They go into conduction and current rises and then falls. And that means during this period of time, T1 and T3 pair is conducting, and load voltage is same as source voltage, and this is the source voltage. This becomes same as load voltage. It is positive from alpha to pi, and from pi to, this is pi plus alpha. From pi to pi plus alpha, this is negative. It has a small negative segment. And that at pi plus alpha, since source voltage has already reversed its polarity, T2, T4 pair is fired. Load again gets connected across the source and it receives the positive segment of source voltage. So load voltage again becomes positive. You see, it is positive from pi plus alpha to 2 pi, a large positive segment, and from 2 pi to 2 pi plus alpha, a small negative segment. And then it repeats. It is again large positive segment and small negative segment, and so on. And previously also there was some small negative segment. So this is the nature of load voltage waveform VA, armature voltage VA. So it has from alpha to pi, the load voltage is having large positive value, and from pi to pi plus alpha, small negative segment. Then again, large positive segment, small negative segment. What happens during these small negative segments? The reactive power, because of this inductance, that is supplied back to the source. During positive segments, inductor stores the energy, and during these negative voltage segments, it releases energy and supplies that energy back to the source. That means there is shuttling back and forth of reactive power in the positive and negative half cycles of the load voltage. During from alpha to pi, there is the flow of reactive power from source to inductance, and from pi to pi plus alpha, that reactive power is supplied back to the source. So it just shuttles back and forth between source and load inductance. Okay. So we have already discussed this. Now, if we can, cancel these negative segments of the voltages, uh, we will be avoiding the flow of reactive power between source and load, and hence we will be improving the power factor of the load, power factor of the source, not load. We will be improving the power factor of the source. For that purpose, let us draw the waveforms again and see how we can achieve that. Again, this is my source voltage, 0, pi, 2 pi, these are the crossings, zero crossings, and so on, 0, pi, 2 pi, and so on. Okay, fine. So this is the back EMF of the motor, EB, and we are firing at same instant. Here, this is alpha, and this is pi plus alpha. This is 2 pi plus alpha, and so on. These are the firing instants. At alpha, T1, T3 pair is fired. At pi plus alpha, T2, T4 pair is fired. At 2 pi plus alpha, again T1, T3 pair is fired, and so on. So the current will rise to reach maximum value here, and then it will start falling, and then it will again rise, fall, and so on. This is the nature of armature current or load current. Okay. Now let me draw the waveforms for gating pulses of different devices. We have 4 devices here. Now gating pulse pattern will be slightly different from what I have drawn earlier for normal operation without freewheeling. In order to achieve freewheeling, the gating pulse pattern will be now like this. This is IG1, that is the firing pulse pattern for thyristor T1. IG2 is the firing pulse for thyristor T2. IG3 is the firing pulse for thyristor T3, and IG4 is the firing pulse for thyristor T4. Okay. Now, the firing pulse for thyristor T1, as usual, it is from alpha to pi plus alpha, just like the previous case without freewheeling. So this is the firing pulse pattern for thyristor T1 from alpha to pi plus alpha in this positive half cycle. In next positive half cycle, also 2 pi plus alpha to 3 pi plus alpha, and so on. So this is the firing pulse pattern for thyristor T1. What about thyristor T2? Whenever for thyristor T2, see, when this pair, when this thyristor is on, at that time this thyristor will be off, and when this will be on, this will be off. So therefore, when from pi plus alpha to 2 pi plus alpha, there will be firing pulse for thyristor T2, because during this period T1 is off. Previously also, the firing pulse for thyristor T2 is like this. What about thyristor T3? In the previous case without freewheeling, the same firing pulse is applied to T1 and T3. I mean, this would have been IG1, IG3, and this would have been IG2, IG4, but it's not the case now. Now, in order to achieve freewheeling, what we will do, the firing pulse for T3 will be different. The firing pulse for T3 will not be from alpha, it will be from 0 up to pi. Okay, it will have a duration of 180 degrees. We will advance it by alpha electrical degrees. In order to achieve freewheeling, I will show you how we achieve freewheeling. So this is the firing pulse for thyristor T3 from 0 to pi, and then from 2 pi to 3 pi. 2 pi to 3 pi. And what about firing pulse for T4? T3 and T4 will be complementary to each other. That means whenever T3 firing pulse is high, T4 will be low. When this is low, this will be high. So since this is low, IG3 is low during this period, so IG4 will be high during this period. So this is the firing pulse pattern. So what I have done, as far as IG1 is concerned, it is same. For thyristor T1, the firing pulse is from alpha to pi plus alpha as without freewheeling. And for IG2 also it is same, from pi plus alpha to 2 pi plus alpha. But for IG3 and IG4, I have modified. Instead of making IG3 same as IG1, I have advanced IG3 by alpha. Okay, it starts from alpha equal to 0, it ends at pi, because duration of pulse is 180 degrees. Okay, and accordingly IG4 also gets modified. Why I am advancing the issuance of firing pulse to thyristor T3? To achieve freewheeling. How do I achieve freewheeling? Let me show you. Let us consider the periods from alpha to pi. From alpha to pi, you know, this is the positive half cycle of source voltage. This is plus, this is minus. So T1 and T3 pair should be fired. Is T1 and T3 pair fired from alpha to pi? Let's try to find that. This is alpha and this is pi. During this period, Ig1 is high and Ig3 is also high. That means T1 and T3 both are fired. They will immediately go into conduction, and equivalent circuit will be like this. This is source voltage. T1 is conducting, it is on. This is the load, and T3 is also conducting because its firing pulse is also high, and source current Is is same as load current, armature current Ia, and this is load voltage, armature voltage. So load voltage will be same as source voltage because load is directly getting connected across the source via T1 and T3, and load voltage is same as source voltage, and therefore load voltage is same as source voltage, and this is our source voltage. It will now become load voltage, armature voltage, from alpha to pi. So from alpha to pi, this is our load voltage VA, and it is same as source voltage. Without freewheeling, you know that from pi to pi plus alpha also load voltage was same as source voltage. I mean, you are getting that small negative segment of voltage, but that will not be the case now because I have altered the firing pulses Ig3 and Ig4. Look what will happen now. From pi to pi plus alpha, Ig1 is still high. That means thyristor T1 will be still conducting. But Ig3 has fallen low. It has become low. So that means T1 is getting firing pulse, but T3 is not getting firing pulse. So T1 and T3 will stop conducting. Instead, what is happening at this instant? Ig1 is high and Ig4 is also high. See, Ig1 is high, Ig4 is high. So that means Ig1 is already high. It is conducting. And now my control circuit is issuing firing pulse to Ig4. Since Ig1 is already conducting, since thyristor T1 is already conducting, T4 will also start conducting, and now whatever energy was stored there in the inductance, inductor will release that energy, and that energy, instead of going back to the source, it will freewheel through T1 and T3. Why? Because T1 and T3 has stopped conducting. Firing pulse to T3 has become low, but T1 is still conducting. And which other device is conducting along with T1? T4, because T4 has also been fired. So T1 and T4 will fire. So inductor will release energy and current will circulate like this. It is freewheeling action. Let me show you the equivalent circuit. So from from pi to pi plus alpha, from pi to pi plus alpha, equivalent circuit will be like this. Thyristor T1 is conducting, T4 will also conduct. This is the load. Inductor is now releasing energy. This is the direction of current. Current will circulate like this. It will flow through T1 and T4. T1 and T4 will short the load terminals. Since load terminals are shorted through T1 and T4, assuming T1 and T4 to be ideal devices, load voltage will become zero. And what will happen to the current? Load current will not become zero. It will freewheel through T1 and T4. This is called freewheeling action. That means whatever energy is released by the inductor in the form of reactive power, that power does not flow back to the source. It is just freewheels, and it is utilized by the machine, and this power is also converted into mechanical power. Okay, so we are, and that way, since the load voltage becomes zero, so what happens from pi to pi plus alpha? Your load voltage is not negative now, it is zero, because load is shorted by these two terminals. Load gets shorted across T1 and T4, and load voltage becomes zero. And since load voltage becomes zero, load current freewheels. And this inductive energy of the inductance, which is released by the inductors, it is also converted into mechanical energy by the motor. So it becomes useful energy. So it is no longer reactive power. It would have been reactive power if it was fed back to the source. It is not fed back to the source. It freewheels. It is converted into mechanical energy. So this is how we can stop the flow of reactive power between source and load, and that way the source power factor will also improve, and there will be better utilization of this power. This power will be converted into mechanical power. It will be used by motor for conversion into useful mechanical power. So this is what happens from alpha to pi and pi to pi plus alpha. Let us see what happens at pi plus alpha. At pi plus alpha, source voltage has already become negative. It has reversed its polarity. T2, now you see, from pi plus alpha to 2 pi, T2 and T4 are high. 2 and 4 are giving firing pulses. They immediately go into conduction and current flows like this. Load again gets connected across the source and load voltage is equal to the positive segment of source voltage. So load voltage is again same as source voltage, positive. What happens from 2 pi to 2 pi plus alpha? From 2 pi to 2 pi plus alpha, Ig2 is still high, but Ig4 has become low. That means T2 is conducting, but T4 has stopped conducting. And T2 का साथ कौन देगा आप? Since T2 is high, T3 also becomes high. You can see T3 also becomes high. T2 के साथ T3 भी conduct करेगा और फ्री व्हीलिंग अब T2 और T3 के थ्रू होगी. T2 और T3 के थ्रू फ्री व्हीलिंग होगी and again there will be free wheeling action. And this reactive power is not sent back to the source, it becomes the useful mechanical power. And load voltage during this period again becomes equal to 0. So this is the load voltage. It becomes 0, then again becomes positive and so on. So that means from this instant to this instant, T1 and T3 pair is conducting. From this instant to this instant, T1 and T4 pair is conducting. T1, T4, and it provides the freewheeling action. From pi plus alpha to 2 pi, T2, T4 pair is conducting, T2, T4, and then from 2 pi to 2 pi plus alpha, T2, T3 is conducting and it is producing freewheeling action. T2, T3, freewheeling action takes place. And previously also T2, T3 is conducting. Previously also load voltage is 0 and T2, T3 pair is conducting, providing the freewheeling action. So therefore, there are no negative segments of the voltage in the load voltage. No negative segments are there. We are cancelling the negative segments. Now this has two advantages. Number one, there is no flow of reactive power. So no reactive power flows between source and load. That improves the source side power factor. And secondly, the average load voltage increases. Why average load voltage increases? Because without freewheeling, your load voltage has this pattern. If you find the average of this waveform, in the average of waveform, the negative segments you have to subtract from the positive segments. So no doubt you will get positive average voltage. On the other hand, if you have this type of waveform, this has higher positive average voltage. This has less average voltage, this has higher average voltage. Why? Because here negative segments you have to subtract. The negative segments cause the average voltage to be less. Since there are no negative segments here during the freewheeling action, the average load voltage is higher. So therefore there are two advantages of providing the freewheeling action. Number one, there is no reactive power flow between source and load during the negative segments of the voltage because we have no negative segments of the voltage. We have cancelled those. Hence, the source side power factor improves. And secondly, since the negative segments of voltages do not exist, the average load voltage increases. So these are the advantages. So we can note down these two advantages. Number one, no reactive power flow. No reactive power flows between source and load. Source and load inductance or load due to cancellation of negative voltage segments. Okay. Second, hence source or input power factor. Input side is AC side or source side. Source side power factor or input side power factor is improved. So there is improvement in the input side or source side power factor. This is number one. And number two, average load voltage increases. Since there are no negative segments present in the load voltage, so average load voltage increases, right? So this is about advantages. So this is how we provide the controlled freewheeling and hence improve the source side power factor and also increase the average load voltage, average armature voltage. What about average load voltage mathematical expression? I will write here average load voltage. Average load voltage VA is given. See here now we have two intervals. First of all, we have powering interval, powering or thyristor conduction interval, thyristor conduction interval. Since I have erased the waveforms, I don't have waveforms on this board, but when you watch this lecture, you will also draw the waveforms, and for you those waveforms are preserved on your notebook. You can refer to those waveforms, and you can find powering interval. Powering interval is from alpha to pi, because if you see from alpha to pi, this is alpha, this is pi, T1 T3 pair conducts, and load voltage is positive. And since during this period T1 T3 thyristors conduct, this is called thyristor conduction mode, or it is also called powering mode, because during this period power flows from source to motor, source to load. Okay, and during this powering mode, what is the load voltage? Load voltage is same as source voltage. You can see load voltage is same as source voltage. So load voltage or armature voltage is same as source voltage. Yes. This is first interval. And what is the second interval? Second interval is from pi to pi plus alpha. From pi to pi plus alpha, T1 and T4 pair conducts. T1 and T4, and it provides freewheeling action. And what is load voltage during this period? Zero. So second mode is freewheeling mode. I will write here freewheeling interval. And freewheeling interval is from pi to pi plus alpha. Pi less than or equal to omega t less than or equal to pi plus alpha, and during this interval load voltage or armature voltage is zero. So with this in mind, therefore average armature voltage or average load voltage, mathematical expression for average load voltage, we can find capital VA means average voltage. If you take 1/2 cycle and integrate it 1 by pi, then integration first from alpha to pi. From alpha to pi, we have powering interval, okay, and during this period, our load voltage VA is same as source voltage. So this is VA, Vs d omega t, because load voltage is same as source voltage. Plus then we have freewheeling interval. Freewheeling interval is from pi to pi plus alpha. So limits of integral are pi to pi plus alpha. And during this period, what is load voltage? Zero. So it is 0 into d omega t. Close the bracket. And now we can simplify this. We can write like this: average armature voltage or average load voltage is equal to 1 by pi. Then integral of this is alpha to pi. Vs is the source voltage. And what is Vs? Vs is equal to Vm sine omega t, because source voltage is sinusoidal. So it is Vm sine omega t d omega t plus 0. So second is 0 because during freewheeling interval load voltage is 0. So this second term is 0. I will not write it. So this is equal to Vm by pi. What is the integration of sine omega t? It's minus cos omega t alpha to pi. So that is equal to Vm by pi. It is minus cos pi plus cos alpha. So average load voltage is equal to Vm by pi. Cos pi is minus 1, minus into minus is plus. So it is 1 plus cos alpha. Or we can, this is in terms of peak input voltage. Vm is the peak source voltage. In terms of RMS source voltage, what is peak voltage in terms of RMS voltage? It is root 2 times RMS voltage. Is root 2 Vs by pi times 1 plus cos alpha. So this is average armature voltage or average load voltage. Without freewheeling, if you remember, without freewheeling, what was the average load voltage? If you remember, it was 2 root 2 Vs by pi cos alpha. And with freewheeling, it has changed. It has now become root 2 Vs by pi times 1 plus cos alpha. These are different waveforms. Okay, these are different expressions. This is without freewheeling. This is with freewheeling. Okay, so this is average load voltage. Now let us try to find the torque speed characteristics. I will again write average armature voltage is root 2 Vs by pi times 1 plus cos alpha. Since we know armature voltage, average armature voltage is back EMF plus IARA. From this, you can find back EMF is equal to VA minus IARA. Okay, and since this torque developed by motor is equal to K phi Ia, which means Ia is equal to T by K phi. So you can substitute here. Therefore, back EMF EB will be equal to VA minus IA. IA is T by K phi. So T RA by K phi. And EB is equal to K phi omega. We know that back EMF is K phi into omega M. It is equal to VA. What is average armature voltage? Average load voltage. It is given by this expression. We already know. So we will substitute root 2 Vs by pi times 1 plus cos alpha minus Ra by phi, K phi into T. So from this, the speed of the motor is given by this expression. Omega m is equal to root 2 Vs by K phi into pi 1 plus cos alpha minus Ra by this K phi will come down. It will become here K phi squared T. So this is the torque speed characteristic of a single phase full converter fed DC motor drive with freewheeling. Without freewheeling, it is different. This is with freewheeling. Okay, and you can now plot these. So that's all about analysis of single phase full converter fed separately excited DC motor drive with freewheeling, uh, assuming a rectification mode of operation and continuous conduction mode of operation. Let us consider discontinuous conduction mode of operation. Let's assume that now the conduction is not continuous, it is discontinuous. Okay, let us draw the waveforms again. This is the source voltage Vs. These are zero crossing points, 0, pi, 2 pi, 3 pi, and so on. And this is minus Vs. Fine. And this is the back EMF, EB. And since we are assuming discontinuous conduction mode of operation, in the discontinuous conduction mode of operation, if you remember, I've already told you that you cannot fire the pair of thyristors, or you cannot fire the converter at those instants of source voltage when source voltage is less than back EMF, because back EMF shows its presence in the load voltage. Back EMF is a part of load voltage, and whenever back EMF is greater than instantaneous source voltage, okay, you cannot fire the converter. You can fire converter only from this point, that is gamma equal to sine inverse sine inverse EB by Vm. This is the point, this point of intersection between EB and Vs, gamma. Beyond this point only you can fire the converter, because beyond this point, say at this point, at this instant of time, instantaneous of source voltage is greater than back EMF, and you can very easily fire a pair of thyristors. Let us assume this is alpha, and then this will be pi plus alpha, and so on. So these are the firing instants. So the pair of thyristors T1 and T3 is fired here. So current will increase, reach peak value somewhere, and then it will decrease and become zero. We are assuming discontinuous conduction mode of operation, so we have to make current zero. Then there is no current. Then again, the other pair of devices T2, T4 is fired here, and current again rises, becomes maximum somewhere here, then falls, becomes zero, then it repeats. Something like this. Previously also, this is the conduction. So this is the nature of armature current. Let us draw the waveforms for gating pulses, because since we have to consider freewheeling also, so gating pulse pattern will be different from that of without freewheeling. So this is Ig1, that is the gate current pulse of thyristor T1. Ig2 is the gating current of thyristor T2. Ig3 is the gating current of thyristor T3, and Ig4 is the gating current of thyristor T4. Gating current pulse will be pattern will be same. I mean, for thyristor T1, it will be from pi to pi plus alpha to pi plus alpha. This is alpha and this is pi plus alpha. And then 2 pi plus alpha to 3 pi plus alpha and so on. And for thyristor T2, mm, it will be complementary of that of thyristor T1. That means when Ig1 is low, Ig2 will be high. It is low here, it will be high. What about Ig3? Ig3 will be advanced. It will not be in synchronism with Ig1. It will be advanced by delay angle alpha. So that means it will start from 0 up to pi. 0 to pi. And then 2 pi to 3 pi. 2 pi to 3 pi. And Ig4 will be complementary to Ig3. So whenever Ig3 is low, Ig4 will be high. So this is the gating current or gating pulse pattern for the four devices T1, T2, T3 and T4. Let's apply it here. Let us consider alpha. Okay, now you can see alpha is greater than gamma because we are firing alpha beyond gamma when instantaneous source voltage is greater than back EMF because of discontinuous conduction mode. At alpha, Ig1 is high, Ig3 is high. So this is the positive half cycle of source voltage. T1 and T3 will be fired, and current will flow like this. Load will get connected directly across the source through T1 and T3, and load voltage will be same as source voltage up to pi. So from alpha to pi, load voltage is same as source voltage. What happens from pi to, let's call this angle as beta. Beta is called extinction angle, the angle at which current becomes zero. So from pi to beta, now you see this is the instant from pi to beta. Ig1 is still high, Ig3 has become low, but Ig4 has become high. So Ig1 is high, Ig4 is high. That means T1 is already conducting, T4 will also start conducting, and there will be freewheeling between T1 and T4. Okay, and since there is freewheeling between T1 and T4, load gets shorted through T1 and T4, and load voltage becomes equal to 0. So this is the freewheeling interval. So I can show the device conduction from alpha to pi, T1, T3 pair is conducting, and from pi to beta, T1, T4 pair is conducting, and from beta to next instant of firing, which is pi plus alpha, no device is conducting because current has already become 0. And since current has already become 0, load is disconnected from the source, and load acts like this. This is the load. It is disconnected from the source. Yeah, आपका source है. It is disconnected from the source because no device is conducting. Now, what is load voltage? Load voltage is not 0. It is equal to its back EMF. If you put a multimeter, voltmeter across the armature terminals, it will read same as back EMF. So load voltage is now equal to back EMF. So it will rise and it will be same as back EMF. This is back EMF. This is EB, back EMF. And during this period, no device is conducting. And then at pi plus alpha, you can see Ig2 is high, Ig4 is high. 2 and 4, since the source voltage has reversed its polarity, 2 and 4 were waiting for firing pulses. 2 is fired, 4 is also fired. They will go into conduction and current flows like this. Load again gets connected across the source, and load voltage is again same as source voltage from pi plus alpha to 2 pi. It is equal to positive source voltage. From 2 pi to 2 pi plus beta, this is 2 pi plus beta. So from pi plus alpha to 2 pi, T2, T4 pair is conducting. From 2 pi to 2 pi plus beta, you can see Ig2 is high, Ig4 has become low, but Ig3 has become high. So 2 is already conducting, 3 will also conduct, and there is freewheeling between 2 and 3, and load voltage is 0. And load voltage again becomes equal to 0. There is freewheeling between T2 and T3, and then there is current becomes 0 and load gets disconnected from the source, and again load voltage is same as back EMF. It is equal to back EMF, and then it repeats like this. Previously also it was equal to back EMF. यहाँ से यहाँ तक load voltage was equal to back EMF, and previously it was zero due to freewheeling action. So this is the nature of load voltage. Now here we can identify three intervals. Instead of two intervals, we identify three intervals. First is powering interval or thyristor conduction interval. Powering interval. Powering interval is from alpha to pi. It is alpha less than or equal to omega t less than or equal to pi. And during this powering interval, you can see T1, T3 pair is conducting and load voltage is same as source voltage. This is load voltage VA. Isn't it same as source voltage? Yes, it is same as source voltage. So VA is equal to VS. What is the next interval? From pi to beta, it is freewheeling interval. Next interval is freewheeling interval. Freewheeling, freewheeling interval. Freewheeling interval is from pi to beta, and during this freewheeling interval T1 T4 pair is conducting and load voltage is equal to 0. You can see load voltage is 0, so VA is equal to 0. And third interval is beta to pi plus alpha. It's called, during this period none of the devices is conducting. Your load is completely disconnected from the source. It is not receiving power from the source. It is not freewheeling also. It is disconnected from the source like this. It's called coasting interval. Third interval is coasting interval. And coasting interval is from beta to pi plus alpha. Beta to pi plus alpha. And during this coasting interval, what is load voltage? It is same as back EMF. VA is equal to EB. So these are the three intervals. Once we know the three intervals, we can very quickly find average load voltage or average armature voltage. So I will write here average armature voltage or average load voltage. Average armature oblique load voltage. It is given by VA is equal to, let's take half cycle and integrate it. First interval is powering interval, that is from alpha to pi. So integration from alpha to pi, and during this period what is load voltage VA? It is same as source voltage, so it is Vs d omega t. Plus second interval is freewheeling interval from pi to beta. So it is from pi to beta, and during this period load voltage is 0. VA is equal to 0. So it is 0 into d omega t. Plus third interval is coasting interval, that is from beta to pi plus alpha. Beta to pi plus alpha, and during this period load voltage, armature voltage is equal to back EMF. So it is EB d omega t. So this is the mathematical expression, and we can very quickly get the mathematical expression for average load voltage. Average load voltage is 1 by pi times integral alpha to pi. Vs is the source voltage, which is equal to Vm sine omega t, and then d omega t, plus second is 0, so second term is 0, I will not write it, plus third term is EB, integration from beta to pi plus alpha d omega t. Okay, so this is it. So this is equal to 1 by pi. If I take Vm outside, what is the integration of sine omega t with d omega t? It is minus cos omega t, and the limits of integration are alpha to pi, plus I have taken EB outside. What is the integration of d omega t? It is d omega t itself, and limits of integration are beta to pi plus alpha. So this is equal to 1 by pi into Vm times, this is minus cos pi minus cosine pi, minus into minus is plus cosine of alpha, plus EB times, so upper integral is pi plus alpha, upper limit is pi plus alpha, minus lower limit is beta. Okay, so bracket closed. So further simplification gives like this. Average armature voltage VA is equal to 1 by pi times, this is Vm, cos pi is minus 1, minus into minus is plus 1 plus cos alpha, plus EB times, this is pi plus alpha minus beta, pi plus alpha minus beta. This is the mathematical expression for average load voltage or average armature voltage, right? This is in terms of peak value of source voltage. In terms of RMS value, it is equal to VA is equal to 1 by pi times Vm is equal to root 2 Vs into 1 plus cos alpha plus EB times pi plus alpha minus beta. So this is the final mathematical expression for average load voltage for a single phase full converter fed DC motor drive with freewheeling. Okay, without freewheeling the expression is different. We have already derived that in one of the early classes. With freewheeling, this is the expression. Now, I would like to develop the torque speed characteristics mathematically. Since VA is equal to, as VA is equal to EB plus IARA, I will substitute that here. So VA is EB plus IARA is equal to 1 by pi times this thing, root 2 Vs into 1 plus cos alpha plus EB times pi plus alpha minus beta. So EB will be equal to 1 by pi into under root 2 Vs 1 plus cos alpha plus EB times pi plus alpha minus beta. So what will happen to this IARA? It will shift to right hand side. It will be minus IARA. Further simplification gives, let us further simplify this. Further simplification gives EB. If you multiply, here LCM is pi, cross multiply, so it will be pi EB. And pi EB is equal to, this will be root 2 Vs times 1 plus cos alpha plus EB times pi plus alpha minus beta, pi plus alpha minus beta, minus this pi will get multiplied to this term also. This will be minus pi IARA, right? Okay, fine. So then pi EB, if I shift it to left hand side, it will be minus EB times pi plus alpha minus beta is equal to, on the right hand side we will get root 2 Vs times 1 plus cos alpha minus pi IARA. So from these two terms I will take EB common. So what I get inside is pi, then here minus pi minus alpha plus beta is equal to root 2 Vs times 1 plus cos alpha minus pi IARA. So plus pi minus pi, they add up to 0. So I get EB times beta minus alpha is equal to root 2 Vs times 1 plus cos alpha minus pi IARA. Fine. From this I can get EB. EB is equal to root 2 Vs into 1 plus cos alpha by beta minus alpha minus pi IARA by beta minus alpha. Fine. Now further simplification gives, since as torque developed by motor is equal to K phi Ia, so this will give me the expression for Ia. Ia is equal to T by K phi. And we also know that EB is also equal to K phi omega m. So substitute E equal to K phi omega m here. So in place of EB, I will write, therefore K phi omega m is equal to, this is root 2 Vs times 1 plus cos alpha by beta minus alpha minus pi into Ra. Let me write Ra first, into Ia. What is Ia? Ia is T by K phi. So this is T by K phi into beta minus alpha, because there is beta minus alpha already here. Okay. So therefore, if I find the speed, So this will finally give me the final expression for speed in terms of torque. Speed of the motor omega m is equal to root 2 Vs times 1 plus cos alpha divided by, so this k phi will divide, this will be k phi times beta minus alpha minus, here we have pi Ra by, so k phi, and this k phi will also come here, it will be k phi whole square into beta minus alpha multiplied by torque T. So this is the final expression, mathematical expression for speed of the motor for in terms of torque with freewheeling action. Okay, so therefore you can just plot for torque speed characteristics. Okay, fine. So this is for rectification mode of operation. For rectification mode of operation, we took two cases. First, we took continuous conduction mode of operation, and then we took the discontinuous conduction mode of operation, and we developed the waveforms, and we also developed the mathematical expressions for average armature voltage or average load voltage, and we also developed torque speed characteristics. Now what about inversion mode of operation? Case B is inversion mode of operation. In inversion mode of operation also there can be two um, modes. Number one, continuous conduction mode, and number two, discontinuous conduction mode. Let us consider first continuous conduction mode. And in the inversion mode of operation without freewheeling, I will write here without freewheeling. The waveforms we have already drawn in one of the early classes. I will just repeat those waveforms. The waveforms will be like this: 0, pi, 2 pi, and so on. And this is minus EB, minus back EMF, because in the inversion mode of operation, the converter has to be operated for alpha greater than 90 degrees. And back EMF also has to be reversed, plus minus. And since we are operating converter in the inversion mode of operation, alpha greater than 90, average load voltage will also reverse. It will be plus minus like this. Okay, so EB has become minus now. Let us assume this is the firing angle, alpha, and then this will be pi plus alpha, this will be 2 pi plus alpha, and so on. And if you draw the gating pulse pattern for IG1 and IG3, IG1 and IG3, you have to fire IG1 and IG3 from alpha to pi plus alpha. This is pi plus alpha. This is the gating pulse pattern for this. And then next will be 2 pi plus alpha to 3 pi plus alpha, and so on. This is for IG1, T1 and T3, IG1, IG3. And for T2 and T4, the gating currents are IG2 and IG4. They are complementary to IG1 and IG2. So it's from here, when this is low, this is high, and then when this is low, when IG1, IG3 is low, IG2, IG4 will be high. So these are the gating current paths. We can very clearly see alpha is greater than 90 degrees. We are not firing below 90 degrees. We are firing above 90 degrees. This is around 120, 130 degrees alpha. And which pair is fired? T1, T3 pair is fired. So immediately the T1, T3 pair will go into conduction and current will start rising. It will rise. Okay. It will rise and then it will fall, but it will be continuous conduction mode of operation. This is armature current IA, is continuous conduction mode of operation. And from alpha to pi plus alpha, T1, T3 pair will conduct. And when T1, T3 pair conducts, load gets connected directly across the source. And load voltage is same as source voltage. And load voltage will be same as source voltage. And this is your source voltage. Small positive segment from alpha to pi and large negative segment from pi to pi plus alpha. So this is the load voltage. And at this instant, at pi plus alpha, T2, T4 pair is fired. Since source voltage has already reversed its polarity, when T2, T4 is fired, current again flows like this, load again gets connected across the source, and load voltage is again equal to source voltage. And where is the source voltage? This is the source voltage. Load voltage is again same as source voltage from pi plus alpha to 2 pi plus alpha, like this. And then it will repeat. And previously also it is like this. So T1, T3 and then T2, T4 pair is conducting. Previously also T2, T4. This is the load voltage waveform. You can see negative voltage segments are much greater than positive voltage. So that average load voltage is negative, because for alpha greater than 90 degrees, VA has to be negative. But because of these small positive voltage segments, during these small positive voltage segments, power will be negative. That means reactive power uh, will be fed back to the source, because the inductor is releasing the energy. So there is shuttling back and forth of reactive power between source and load. If we can omit or cancel these small positive voltage segments and cause freewheeling action, then there will be no flow of reactive power between source and load. There will be freewheeling action, and whatever energy was stored in the inductance, that will be used and converted into useful mechanical energy, and that will improve the source side power factor, and average load voltage will also increase. It will become more negative for a given delay angle or given firing angle. How can we do that? How can we go for freewheeling? Now, with freewheeling, now I will write here continuous conduction mode with freewheeling. FW means freewheeling. Let us draw the waveform. The firing pulse pattern has to be altered a bit. That will automatically give you this freewheeling action. This is the source voltage waveform, positive Vs, and this is negative Vs, 0, pi, 2 pi, these are the zero crossings. And this is the back EMF minus EB. And again, let's assume alpha is greater than 90 degrees. So this is alpha. So obviously this will be pi plus alpha. This will be 2 pi plus alpha. These are the firing instants. Let me now show you the gating pulse pattern. The gating pulse pattern will be different now for freewheeling. I will draw for all the four devices separately. This is IG1, that is the gating current pulse for thyristor T1. IG2 is the gating current pulse for thyristor T2. IG3 is the gating current pulse for thyristor T3. And IG4 is the gating current pulse for thyristor T4. Okay. For thyristor T1, the gating current pulse will be from, it will get altered. It will not be from alpha to pi plus alpha, as was case with rectification mode of operation. It will be from pi to 2 pi. Let me show you first. It will be from pi to 2 pi. And then 3 pi to 4 pi and so on. What about IG2? IG2 will be just complementary to IG1. That means whenever IG1 is low, IG2 will be high, like this. And what about IG3? IG3 will be from this instant to this instant. Say from this firing instant to next firing instant. From here to here. IG3. Similarly, then here also from here to next. Okay, fine. And what about IG4? IG4 will be complementary to IG3. So since IG3 is low during this period, IG4 will be high. IG3 is high during this period, IG4 will be low. IG3 is low during this period, IG4 will be high. So these are the firing pulse patterns for all the four devices. Let us analyze it now. Let us see what happens from pi to pi plus alpha first. Pi to pi plus alpha. From pi to pi plus alpha, that means from this instant to this instant. IG1 is high, IG3 is high. 1 and 3 both are high. And your load voltage is same as source voltage. Since source voltage has reversed its polarity, load voltage is also equal to source voltage. So load voltage is same as source voltage. because T1 and T3 will conduct, load will get connected directly across the source. Since source voltage has already reversed its polarity, load voltage will be same as source voltage and it's negative. So during this period, T1 and T3 pair is conducting. अच्छा, उसके बाद from pi plus alpha to 2 pi क्या होता है? There would have been positive segment of voltage, but we want to cancel that positive segment of voltage. What happens from pi plus alpha to 2 pi? You can very clearly see Ig1 is still high, but Ig3 low हो गया, but Ig4 high हो गया. 1 is high, that means T1 already conduct कर रहा है. Now 4 is also conducting. 1 and 4 will conduct and freewheeling action will take place like this. Freewheeling action हो जाएगा. और जब freewheeling action हो जाएगा, what will be load voltage? Load voltage, instead of becoming positive like this, it will drop to zero, because during the freewheeling action, load voltage becomes zero. So load voltage becomes zero. Okay. So therefore current का क्या होगा? Current fall हो जाएगी, freewheeling period के दौरान high हो जाएगी, and then again fall high. This will be nature of armature current. It's continuous conduction mode of operation. अच्छा, then what will happen at 2 pi? 2 pi पे source voltage अब positive हो गई, right? This is it's plus minus, and which pair of devices is conducting? This is 2 pi. Ig2, this Ig2 is high and Ig4 is high. यहाँ से यहाँ तक 2 और 4 high हो रहा है. यहाँ से यहाँ तक, यहाँ से यहाँ तक. Let me first write T1 T4 are high, and then T2 T4 high हो रहे हैं. T2 and T4 चूंकि high हो रहे हैं, and this is the load voltage. ये load voltage फिर से negative जा रही है. It's again becoming negative. T2 T4, क्योंकि ये प्लस है, ये माइनस है, सॉरी, सोर्स वोल्टेज ऑलरेडी पॉजिटिव हो गई है, बट लोड वोल्टेज नेगेटिव हो जाएगी. दिस विल बिकम नेगेटिव एंड दिस विल बिकम पॉजिटिव. So load voltage again becomes negative. What happens from this to this instant? T2 still high है, लेकिन T4 low हो गया, लेकिन T3 high हो गया. 2 high है, 3 भी high हो गया. 2-3 pair will conduct और freewheeling action होगा. और during freewheeling action, load voltage becomes zero. इसका मतलब previously B. So during this period, T2 T3 pair is conducting. That means previously B, T2 T3 pair was conducting and load voltage was zero. और उससे पहले load voltage negative थी, क्योंकि T2 T4 pair was conducting. So this is the nature of load voltage. You can see load voltage is negative 0, negative 0, negative 0. It's nowhere positive. The positive segments have been just cancelled because of freewheeling action. And hence there is no reactive power flow between source and load. The source power factor improves, and since these positive voltage segments have been cancelled, the average load voltage becomes more negative. I mean, the average load voltage magnitude increases. So this shows inversion mode of operation. Here also you have two modes. You have thyristor conduction mode and you have freewheeling mode, and average load voltage waveform, average load voltage expression is same, which I have already derived for rectification mode of operation. That remains same. Now you can try it for discontinuous conduction mode of operation. I leave that to you as an exercise. Just draw the waveforms for discontinuous conduction mode of operation with freewheeling. And as far as mathematical expression and torque speed characteristics are concerned, we have already derived those for rectification mode of operation. Those will remain same. So therefore, with controlled freewheeling, for a single phase full converter feeding a separately excited DC motor drive, we can achieve two objectives: whether the drive is operating in rectification mode or in inversion mode of operation, the average load voltage increases, and secondly, the supply side or the source power factor improves. So with this, I will end my today's lecture. More on it in next lecture. Thank you.